Hello and welcome to episode number 15 of CS350 Online. I'm your host as always, Leslie Eisted, and on today's episode we're going to talk about how the kernel uses virtual memory, and then we're going to round up our discussion of virtual memory by talking about on-demand paging, which is something that many modern operating systems do to support more processes in memory than they could technically fit. But first, it's time for the operating system of the day. So our OS of the day is called QNX, and this is one that you might have heard of, or at least I hope you've heard of, because this is actually a local operating system. So back in 1982, there were these two students who were taking trains. I don't know what the name of the course actually is. It's the trains course. And their names were Gordon Bell and Dan Dodge. And while they were taking this course, I guess they got thinking, it would be nice if the world, the actual real world, had a real-time operating system instead of just creating one to drive a bunch of toy trains around a track in a room isolated on the third floor of MC. So they went out and they actually built a real-world, real-time operating system, and they called it QNX. Now, this is a Unix-like operating system. It is real-time, which means that there are stricter guarantees on how much time it takes for the operating system to respond to events and so on and so forth. And it's also a microkernel operating system. What that means is the bare minimum of things are going to be in the kernel itself, and most things are actually going to be user processes. So in particular, this microkernel OS actually contains only interrupt redirection. You'll notice it didn't say handling, interrupt redirection. It contains timers, a CPU scheduler, and inter-process communication. And everything else at the time was actually achieved through things like message passing. Now, the original operating system was actually only 44 kilobytes, which is actually really impressive. It's impressively small. And when you have an operating system that's this small, what you tend to see it used for as embedded operating systems, which means that people will put the operating system actually on a hardware chip, and it operates really, really quick, and you don't have to worry about secondary storage and so on. So it's quite common as an embedded OS. And it's been used by many, many people. So originally the Ontario School Board started to use it. And I mean, I've seen how things like that work. They're like, hey, we should use Canadian software. But where you really see QNX being used is in any kind of industrial application, and in the aircraft and automobile industries, you'll see QNX used a lot. And of course, BlackBerry, RIM, whatever you want to call it, actually bought out QNX, and they've been using that as part of their operating system for a while. But you also see QNX on millions and millions of vehicles. And carrier-grade routers, you'll see it in infotainment systems. And I almost cringe at using that word, but like the little car consoles that actually tell you a bit more than just what speed you're going. A lot of them actually run QNX. So you're also going to look at any kind of robotics. It's a great operating system for controlling robots because it is a real-time operating system. And you want to make sure that the robots don't, rise up and try to attack everybody. All right. So we left off last day. We were talking about virtual memory. And in particular, we had just finished a discussion of how does that address space actually get the size? How does it get the segments? How does it know that the code segment should be so many megabytes and the data segment should be so many megabytes? Where does that information actually come from? So just to kind of remind you about it, there's this wonderful application that you can run. Switch over here so you can actually see it a bit better. And this actually exists, by the way, on your computer if you have GCC installed. And it's the object dump, and we've made it human readable. We're looking at the header. And in the header of that binary file, you actually see all of the information needed to populate the address space. So what we've got is the information for the text segment, which is the code segment. and you'll see that it's marked as read-only. You can see how big it is. You can see where in virtual memory it's going to go, and you can see things like where in the file it is. And then you've got things like read-only data, which will be paired right up against the code segment. And then we've got the data segment right here, and you'll notice that it's missing the read-only flag, and it tells us, where to put it in virtual memory and how big it should be, where to find it in this file. So all of the information you need to create an address space is actually contained in the binary file itself, with the exception of the stack, of course, because the stack is usually determined by the operating system. And in fact, that's actually quite common. If you look at OS 161, we use the stack located in a fixed location in the user address space, and it's the same for every single process. And then for the size of the stack, we've set it to 48 kilobytes. That's 12 pages. Now, that may seem really small, but if you think about OS 161, that's probably not too bad, actually. Now, on modern operating systems like Linux and Windows and macOS, you're looking at a default stack size somewhere around 1 or 2 megabytes. And it's not to say that it can't grow out of that. There certainly can be system calls that ask for the stack to grow, but that is the default stack size. Now, that kind of ends where we left off. And what I want to talk about now is, now that we've finished kind of talking about how the address space gets its size and its shape and its content, one of the things that we really haven't talked about is what kind of memory does the kernel actually run in. And up until this point, you might have thought to yourself, well, the kernel just runs in physical memory. All of the kernel's addresses are physical addresses. But, it would be really nice if we could abstract ourselves from that. Because think of it this way. We don't really want to use those physical addresses. Let's say the kernel has to use some fixed region of addresses, and maybe the computer you're running on doesn't quite have that. So it would be really nice if we had some way to also run the kernel in virtual memory. Also, good abstract design and so on and so forth, an added layer of security. But how do you do this? Because one of the big problems with running a kernel in virtual memory is the fact that the kernel is responsible for implementing and managing virtual memory, even while it's booting. So how is the kernel going to run in virtual memory when it's booting up? And we call that the bootstrapping problem, and the solutions to that are architecture specific. Now, in our MIPS case, one of the things that we're going to do, one of the things we're going to do is the MMU actually can recognize a user address from a kernel address. And if it sees one of these kernel addresses, it will use a different address translation scheme. And if it sees a user address, it will use the user scheme. And what's interesting is when you are actually running the CPU in an unprivileged mode, you won't be able to translate successfully any of the kernel's addresses, because it'll see that address and it will know that it's not in the range, and furthermore it'll be like, yeah, I can't translate that. So bootstrapping is solved in an architecturally specific way. As you're going to see in a minute, our MIPS architecture, our MIPS architecture is actually using dynamic relocation for the kernel. Now, the other problem is the sharing problem. So let's suppose that every process and the kernel are all using virtual memory, and every single one of them are using the range 0 to the end of memory. Well, if I want to then copy data from one of these address spaces into another, how do I do that? Because it suddenly becomes really, really difficult. Because if I just do mem copy dead beef to A5, 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 I mean, that's just going to copy it from dead beef from A to A5, 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 A5 in my own address space. So how do I actually facilitate data being transferred from one virtual memory to another? So the sharing problem is actually, it has an interesting solution. And this is something that we actually do in real operating systems. And that is, we're going to subdivide the total virtual memory space into two. And we're going to set aside 50% of it, sometimes the value changes, for the user processes to use. And the remaining part is going to be used for the kernel. So in OS 161, we do a 50-50 split, and that's actually the most common division of virtual memory. So like Windows and I think the default Linux one and Mac OS all do a 50-50 split. And the idea is that the lower 50% will be user addresses, and then the upper 50% will be for the kernel. And if you're wondering, how do I know when you get these TLB panics? How do I know whether it's the kernel or whether it's a user address? Well, it's that virtual address that's given to you that tells me what's going on. So if you have an address that's less than or equal to this number here, I know it's a user space address. And I know if the address is greater than or equal to this one here, I know that you actually have the memory problem coming from the kernel. Oh, I don't know why I'm so tired. And again, this is something, it's not just OS 161 that's doing this. This is also something that all major operating systems do it. 50-50 is the most common split, but you'll also see like 25-75 and maybe 1/3, 2/3. Other splits are possible, but 50-50 is the most common. All right. So on that note, maybe we should take some time to look at exactly how OS 161's virtual memory and physical memory work, which is a bit of a discussion of how the architecture is going to translate things and kind of a bit of a discussion of MIPS and OS 161. So as you remember, that if you have user processes, even though the operating system uses segmentation, remember that the MMU is actually a paged MMU, but that's only for the user. So here's what we're going to do. So we have 32-bit virtual addresses, so here's our 32-bit range, and we have 32-bit physical addresses as well. Unfortunately, SYS161, even though we use 32-bit physical addresses, SYS161, our simulator, actually only supports up to 1 GB of physical memory. But if you look at the little programs that we've been running, that really shouldn't be a problem. So you shouldn't see any physical addresses beyond this one right here. Now, then if you look at how virtual memory is laid out, we're doing a 50-50 split. So the lower 50%, which is 2 GB, that is going to be for the user. And then the upper 50% is going to be for the kernel. Now, the user's virtual memory is going to be paged. And we're going to map that to frames of physical memory. And it's also going to be cached. That is, it's going to make use of the TLB, and we'll talk about that in a minute. And then if you look at what's interesting is if you look at the kernel's virtual memory, it is also segmented. And it is segmented into 3 chunks. You've got ksig0, ksig1, and ksig2. So ksig0, this is actually where the kernel's address space lives. It's 512 megabyte chunk. That's where your data structures, your heap, and the stacks for all the kernel go. Then you have ksig1, which is used for addressing devices. We'll talk about that a little bit today, and then in a few days we'll talk about it in greater detail when we talk about how devices work. And then you've got ksig2, which is not used, and it's 1 GB in size. Now, this is not just a restriction coming from OS 161 and SYS161. This is actually coming down from the R3000 spec. They didn't use this remaining gigabyte. So, as I said, the user virtual memory is going to be paged, and it's going to be cached using the TLB. Now, what's interesting here is this memory. How does the operating system know when you create a virtual address space? How do you know which pages of physical memory are actually free for the user program to use? How do you know that? Well, there's actually an answer. It was on the previous slide, and we'll talk more about it when we talk about assignment 3 in maybe a week or so. So what's going to need to happen is your operating system is going to need to have what's known as a core map. And a core map is going to have an entry for every possible frame of physical memory in the system. And for each of those entries, we're going to indicate whether or not it's free. And then when the user program, whether it's allocating the space needed for the code segment or what have you, whenever you want to make an allocation, you will ask the core map. You say, core map, please give me so many things. And the core map will search itself and return to the address of whatever memory you requested if it's available, or will return some kind of error code to indicate that there's no memory available to satisfy your request. So the operating system keeps this core map structure to keep track of what memory is available and what memory is not available. And it's a very cool thing. You're going to get to implement one. We'll talk more about it later. So our user addresses, they're going to be paged, and they're going to be frames, and they're going to be cached in the TLB. But what about the kernel's virtual memory? Because we've talked all about paging before and all about segmentation. We know about that. But how does the kernel do it? So the kernel, as I said, is using kind of a form of dynamic relocation. So when the MMU sees a kseg0 address, and kseg0 goes from this address here, 8, to A, and A is going to be the limit there. So that's a 512 megabyte range, and it maps to the first 512 megabytes of physical memory. Now that doesn't mean it uses the whole 512 megabytes, it's just this block of virtual addresses would map theoretically to these block of physical addresses. In reality, we use a very small amount of kseg0, only a few megabytes at the top. And then we have, so that's our kseg0. So in order to do the address translation, to go from kseg0, the virtual address, to a kseg0 physical address, you subtract the offset, which is the starting virtual address. So you're going to add or subtract this depending on which direction you're going. Now, I will note that the TLB is not used. We are not using any kind of caching for these addresses whatsoever. Now, kseg1 then is also a 512 megabyte chunk, and it goes from A to C. And it also maps to the first 512 megabytes. Now, this is where people get very confused because you've got two separate segments of the virtual address space mapping to the exact same region of physical memory. And you might be thinking, well, I can't store two things in the same spot of physical memory because they're just going to overwrite each other. And you're right. But kseg1 is not an address space. kseg1 is realistically used for the devices, and only a teeny tiny part of it is actually used. And the operating system knows that that range is used, and so the kseg0 range will just avoid using it. Now people say, well, what if you need the whole amount of space? And I want to remind you that while it seems like an operating system for this might use the whole 512 megabytes, we are not talking about a modern operating system here. We're not talking about a modern CPU setup here. We're talking about a system from the early mid-90s. And let's just say this. So I had Windows 3.1 in the early mid-90s. And Windows 3.1 was 4 floppy disks, and each floppy disk was 1.55 megabytes. So you're talking about the total installer being less than 8 megs. So you can't tell me that the operating system, once installed, magically inflated to 512 megabytes. It just didn't. For this particular era, this was an appropriate size, and kseg0 and kseg1 would not overlap in reality, even though their virtual addresses do map to the same physical range. And we will show you which of kseg1's addresses are actually used when we talk about devices. So to do this translation, again, you're going to subtract the offset. So in this case, you're going to subtract this number here, A0000000. Subtract that, and that'll take you from a virtual address to a physical address. And again, the TLB is not going to be used here. So for KSIG 0 and KSIG 1, we are not using the paging system. We are not using page table entries. We're not using that TLB. KSIG 2, we don't have to talk about how it's translated because it's simply not supported. All right, so I'd like to take a moment here then, and normally I would give you a sample problem and give you a couple days to try it, but since we're going to be moving on to a new topic in episode 16, I'd like to just do this problem here with you right now. So if you have access to Piazza and the sample problems there, this is MIPS Translate. So what this question is asking you is, given our MIPS system as we've just described it, and our typical page size of 4 kilobytes, and we've been given a page table as well, we've got, a bunch of physical addresses here. There's 4 of them actually. And we want to know not which specific virtual address translates to this physical one. We want to know what are all of the possible virtual addresses that could translate to this physical one. So let's take a look at them. So I'm going to make this a little bit bigger over here. We note that the first 512 megabytes of physical memory corresponds to a KSIG 0 or a KSIG 1 address. And I'm going to tell you that that puts a limit at the following address. So anything that is less than or equal to that is within the first 512 megabytes. So when you look at each of these 4 physical addresses here, you'll see that they actually all lie in the first 512 megabytes of virtual memory. It's great, right? So that means for each of these addresses, they could have come from a KSIG 0 or a KSIG 1. So let's fill those in first. So for the first one, I'm going to use a regular expression here just to save time. To go the other way, this is 8 or A. So to go from physical back to virtual, remember, we would be adding. And I'm going to leave some space here. All right. So as it turns out, since all 4 of these physical addresses actually lie in the first 512 megabytes, all 4 of these addresses could have been a KSIG 0 or could be a KSIG 1 virtual address. But the thing that we haven't taken into consideration yet is this page table over here. Could any of these physical addresses have been translated from one of these pages? So we're not going to be doing a page number lookup. We're going to be doing a frame number lookup. We're going to go backwards. There's the table a bit better for you to see. So I know that because I have 32-bit physical and virtual addresses and 4 kilobyte pages, I know that my page and frame numbers are actually going to be 20 bits, and that's the first 5 hex digits because each hex digit is 4 bits. So I'm going to look up the frame number 01113 in the table, and I find it, and I see that, yes, it maps to a valid page number, which means that the first physical address also could have come from the following virtual address. So I'm going to replace the frame number with the page number. So there we go there. And then I'm going to look up the next one, 0100A, and I found that as well. So that one could also have come from, trying to draw a bracket here, and I don't mean to draw a bracket. That's actually a really fun address right there because I think it's 400,080, or it could be 400,088, which is actually the address of common exception. Don't ask me why I have things like this memorized, I just do. Now let's look up our next frame number, which is 0100B, and I look that up in the table and I don't see it, which means that we don't believe that there is any other virtual addresses which may currently be using that. And then we have D here, 08343, and that is definitely in the table. So the other possible virtual address that could translate to this one here is going to be 1000FFC. So there you go. Those are all of the possible virtual addresses that could map to each of these physical addresses. Now remember, we're not saying which one is actually doing the mapping. We're just asking, given this setup, what are all of the different possibilities? Keep that in mind. All right. That actually concludes our discussion on kernel virtual memory. I couldn't resist. Since we had QNX as the operating system of the day, I had to try to find the oldest BlackBerry commercial I could find. Which actually, that one wasn't as old as I was hoping for, because I think that when they were actually still called BlackBerry. I can tell you though, when I started my undergrad, it was called RIM and not BlackBerry. And they were all the rage. Like Apple cell phones, totally not a thing. Nobody cared about them. And things like Android cell phones, nobody cared about them. It was all about the BlackBerry phone. All right, so now we're moving on to the last topic for virtual memory, and that is this topic of on-demand paging. So here's the thing. With the implementations of virtual memory that we've given you so far, you have a lot of restrictions. For example, you can't, since we preload the address space, when you run out of physical memory, you actually can't load any more processes. So if your computer only has 8 gigs of RAM and you try to load MATLAB, which takes like 5 gigabytes for its address space, I might be exaggerating. But let's suppose MATLAB does take 5 gigabytes. It's certainly not small. That means that you can only open one copy of MATLAB and maybe your Chrome browser, maybe, with one tab. But who wants to have just 2 programs running? We would much rather have thousands of programs running and be able to, listen to music while we are watching our lecture episodes, while you are writing code and chatting with your friends. And if you want the ability to do all of those things at once, then we need the ability to support more processes running than we technically have physical memory to support. And at the same time, we also want the ability to run MATLAB on computers that only have 1 gig of RAM. How do you support that, where you have the total amount of memory needed by the processes you're running is bigger than the amount of memory you actually have? That's actually where on-demand paging comes in. Because the idea is, if you look at a program like MATLAB, which is a massive, massive program, it has lots of things that most people aren't even aware exist. Believe it or not, MATLAB actually has a built-in translator, and it will take your MATLAB code and it will produce the equivalent C program, and it will spit it out, and you can compile and run the C program that's equivalent to what you did in MATLAB. Crazy, right? Most people don't know that exists. And then you've got all kinds of things, like you've got these different packages for waveform analysis and so on and so forth. Whereas most people just open it up to multiply 2 matrices together. Okay. So does it really make sense then, when you load MATLAB, to load 100% of the program's code and data into physical memory if you are only ever going to use like 1% of it? Looking at even an operating system, if you look at Linux or Mac OS or Windows, the vast majority of the code that makes up these operating systems is not kernel code. It's driver code. It's drivers for Dvorak keyboards. It's drivers for Sound Blasters from the early 90s. It's drivers for Hercules graphics cards that no one even knows what those are anymore. It's drivers for Matrox cards. People don't generally have that hardware. And so even though the drivers are there, why would you load those into memory if you are not going to be using them? This is the point of on-demand paging. We can actually really conserve how much memory we're using if we only ever load the page that we need at the point that we need it. So we start out with an empty address space, and we only start loading elements into the address space as we try to access addresses on those pages. So we don't even start loading the program until we actually start running the program. And on that first translation where we're trying to, translate the starting address, we'll load the page that contains the start address. The advantage here is that means that the address space actually resides on secondary storage. So programs that are running may only actually occupy a couple pages of physical memory, which gives us the ability to run significantly more programs at the same time. And it also gives us the ability to run bigger programs than we can physically support. Now, the downside, because it's not all upside, the downside is that we're going to have to be going to secondary storage. And that's kind of slow. We'll talk more about that in a moment. All right. So in order to make this all work, we're going to need to modify our understanding of page table entry. We need to add something called a present bit. The whole goal of the present bit is to indicate whether or not a particular page is actually in physical memory or not. So we add the present bit, and if the present bit is 1, it means this resides in physical memory right now, which means that it is a valid page to frame mapping, and the frame is an actual real thing. Now, if you take all of the virtual pages that are in physical memory right now, we actually call that the resident set. So all of the pages whose present bit is 1, that is our resident set, because that is what is lying in memory right now. And the problem that you're going to end up with is, what if you only have 3 physical frames of memory? You're going to actually have to do a lot of page swapping. So let's say that your process has all 3 frames filled. Then when you try to load the next frame in, well, your cache, which is now physical memory, is full, and we're going to have to choose somebody to evict. So we're going to be swapping in and out pages in and out of the resident set as the programs execute. Now, what's interesting is you can have, so if the present bit is 1, valid should also be 1. And that means that the frame number is set and it is a real frame number. That means page is valid, it is in memory. If the present bit is 0, that doesn't mean the page is invalid. And in fact, if the present bit is 0, you can have the valid bit as 1. What that means is this is a valid page in the address space, but it's not in memory yet. So the frame number in the page table entry isn't real, it's garbage. And the reason why the frame number would be garbage is because that page hasn't yet been mapped into physical memory. And we can't do this translation until we assign that frame number. Now, if the valid bit is 0, we don't even care what the present bit is because it's simply not a valid page of our address space. So now we have to talk about this concept of page faults, which I'm sure if you dig back, you might remember this from CS350. But here's the idea. Now, the MMU doesn't really know that this is going on. What we're going to do is that your TLB, on a software managed TLB, what's going to happen is that you don't see this as being a page fault. You're going to see this more as a TLB miss. You should never have a page to frame mapping in the TLB that is not, whose present bit is 0, because that doesn't make sense. The point of the TLB is to make the address translations fast. So if you have a TLB entry where the present bit is 0, then you actually can't do anything with that TLB entry. It's a waste of space because the frame number doesn't exist. So you have to throw an exception anyways. So the contents of the TLB should always have the present bit set to 1. So when you're going to detect that something isn't actually in physical memory is through a TLB miss. So you get a TLB miss, and in a hardware managed TLB, it's actually going to have to check that present bit, and when it sees the present bit is 0, it will throw a specific exception for the kernel. But on a software managed TLB, we don't need to do anything different, because on the TLB miss, what's going to happen is the kernel would be involved anyways. And then the kernel would, of course, need to then try to look up the page table entry and add it to the TLB, and when it looks up the page table entry, it notices that the present bit is 0. And so then the kernel says, oh, this TLB miss was actually a page fault. And so the kernel is then going to have to find the appropriate page of the address space from secondary storage, and it's going to have to find a frame to copy it to, or maybe even evicting somebody so that you can insert yourself. And then once you've swapped yourself into physical memory, we can update the page table entry with the frame you just copied yourself to, and then we can update the TLB, and then we can retry the address translation. So in our software managed TLBs, page faults are detected through TLB misses. Now, I said that these page faults, when you have to do the swapping, it's really expensive. It's the downside of on-demand paging. And it really comes down to how often do you actually perform one of these swaps. So when we say what we're going to compare the performance to is a traditional OS 161 style address space preloading, where the whole address space is loaded when the program is loaded and it stays in physical memory for the duration of the program's lifetime. So that is going to be our gold standard for performance. And why is it the gold standard for performance? Because everything is in RAM, which means that we never have to go to secondary storage after the initial load. So the thing you have to know about secondary storage is it's orders of magnitude slower than accessing RAM. So you could be looking at milliseconds or microseconds as compared to nanoseconds for RAM. So if we make the assumption that accessing secondary storage is 1,000 times slower than RAM, which is a pretty good assumption to make even with an SSD, then we can kind of estimate the impact on the performance of the program as compared to address space preloading. So if you have a page fault for every 10 memory accesses, then your program is 100 times slower. 100 times. So if your program on OS 161 took 1 minute, it now takes 100 minutes to run. 100 minutes. I don't know about you, but if I have to wait more than like 10 seconds, I throw things out the window because I get irritated with them. Page faults are bad. If we have one page fault for every 100 memory accesses, then we're only 10 times slower. So instead of 1 minute, now we're 10 minutes. One in every 1,000 memory accesses, only twice as slow. So now you're seeing here the impact of having these page faults. It's a really, really costly thing. We get great benefit out of on-demand paging, but it comes at a cost of performance. So what we really need to do is minimize the number of page faults that actually occur. And there's various things that you can actually do. You can hide the latencies associated with page faults by doing prefetching. So you can predict what pages you're going to need in the future based on what pages you are currently using right now, and that's because of locality. Talk about that soon. Problem is, if you have a single CPU system, you'd be taking time away from the user program to perform the prefetch. Now, prefetching works on a multi-core system because you can kind of dedicate one core to doing prefetching, but we won't get into that. And in fact, by the way, there are architectures that actually have cores set aside specifically for this purpose. In fact, the latest Spark architectures have, I think it is 2 cores actually set aside for the OS and doing things like prefetch. We don't have that on our modern CPUs that we use in our own computers. But that's not to say the OS can't choose to do that. What we're going to talk about instead is, can we be smart about this? Can we actually choose some kind of cache eviction strategy such that we don't evict pages from RAM if we think we're probably going to use them in the near future? And that's what we're going to look at now. So the most boring and easiest to implement for a replacement policy. Now, these policies, we're talking about them from the perspective of how do you choose which frame of physical memory to swap out to support the new page. But all of these methods we're talking about can be used for cache eviction strategies as well. So this is not something that's restricted to just being used for physical memory. So of course, the oldest, easiest way to do things is first in, first out. So when you run out of space, you simply kick out the oldest one. All right. So what we have here is a very restricted physical memory. It's got 3 frames. And we've got a bunch of memory references, and it indicates which page we are going to access. So we start, and then at the bottom, an X indicates there's a page fault. So we started out with an empty physical memory, and then we tried to access something on page A. So that caused a fault and caused us to load page A into frame 1. Same with B and same with C. But when we come to the 4th memory operation, we're trying to access something on page D, but D is not in memory. It's not present. And so we get a page fault. And when we try to load page D into physical memory, we realize there's no space. So now we have to choose one of A, B, or C to evict. Well, A is the oldest, so we kick A out. But unfortunately, memory operation number 5 was going back to page A. Oops. So we kick out B. And then in memory operation 6, we access B, so we kick out C. And you can see here, while this is very simple to implement, we actually end up with a lot of page faults. Maybe not the best idea. So what is the best that you can do? What is the absolute best page replacement algorithm? Well, there's one called optimal page replacement. An optimal page replacement says, okay, I will choose to evict the page that I'm not going to use for the longest time. So we still have the initial 3 faults, and we still have the 4th fault, where we have to choose one of A, B, or C to evict to insert D. But here's what I'm going to do. I'm going to say, which of A, B, and C am I not going to use for the longest time? So I notice I'm going to use A right away, and I'm going to use B right away. But I don't use C until operation 10. So C is the safe one to evict. So I evict C and I insert D. Hit, and I don't get a miss until operation 7, where I try to access page E. And again, I'm going to evict one of A, B, or D, which I don't use for the longest time in the future, and that's going to be D. So I then get hit, miss. Significantly less page faults than the previous one. Pretty good, right? Impossible. Because you don't know the future. Well, presumably you don't know the future, but your computer sure doesn't know the future. Your computer doesn't know what memory operations are going to go next because it hasn't executed those lines of code yet. So it doesn't know what's going to happen next. So optimal page replacement, yes, we know what it is theoretically, but we can't actually implement this. But the question then becomes, can we estimate this? Can we make an intelligent guess as to what we're going to use next? And the answer to that is yes, actually you can make an intelligent guess. And I'd like to, instead of showing you this slide, I'd actually like to just draw it out for you. There's my pen. So let's suppose that you have a program. And let's write it as its assembly. So this is just a bunch of assembly instructions here. Okay. This is in sequential order. So this is 1, 2, 3, 4. I don't know how many I wrote this time. 8, 10. Nice round number. Okay. Ask yourself, what is the probability that these 10 sequential instructions live on the same page? Oh, it's pretty high. But also ask yourself, if it's not existing on one page, then at most this sequence of instructions lives on 2 pages. And we know that because this is a sequential program, that those 2 pages of virtual memory will be sequential as well. So pages near where we are right now are very likely to be used near where we are. So if we are using addresses on page 1, and we've done a lot of things on page 1, then it's very likely we're going to do stuff on page 2. That's spatial locality. We also have this concept of temporal locality, which is the idea that if we've used page 1 a lot recently, then we're probably going to be using page 1 a lot in the near future. So spatial locality takes advantage of the fact that Code tends to be sequential, both code, but then things like arrays as well. And temporal locality is looking at the fact that things that we use recently, we're very likely to use again. So we're not going to so much deal with spatial locality, but let's actually look at temporal locality. So can we exploit these concepts of locality to predict which pages are safe? So there's this one called least recently used. Now I'm going to tell you that this little example that we have in the slides isn't really a great example. And in practice, least recently used does do better than first in, first out. But the idea between least recently used is we are always going to choose to evict the page that was least recently used. It just so happens that in this case, we end up evicting the exact same thing as before. So we have faults on A, B, and C, memory operations 1, 2, 3. On the page fault for D in memory operation 4, we ended up evicting A. And that's because it was the least recently used. Again, this is a bad example, but it does show you how least recently used works. Now, the interesting thing about this least recently used is that you can't really implement this either. Let me explain why. So in order to keep track of least recently used, we have to know how every time a page to frame mapping is used. So every time you translate something on a page, we need to keep track of the fact that you just did that. In order to keep track of every time a successful translation happens, we probably want the kernel to do that. But at the same time, we don't want the kernel involved in every translation. The kernel doesn't know about successful translations because the MMU just handles it and we move on. We didn't want the kernel doing the translation because it would be too slow. So in order to do LRU directly, we would actually have to go back to a model where the kernel was directly involved with every translation, which we don't want. Now, you might be thinking, well, couldn't we modify the hardware such that each will add to the page table entry the time we used it? Well, now the MMU has to talk to the clock, and now we have to add, a 4-byte or longer field to keep track of the time, or maybe it's a register you've got. Do you see what I mean? In order to implement LRU in hardware, we'd actually have to modify our hardware a fair bit. And that may be logic that you don't want to spend the money on. So LRU, because we don't keep track of successful translations, we only get the kernel involved on failures. LRU really isn't used in practice directly. It's not to say it couldn't be, it's just in practice we don't do it because we don't know about successful translations. Can we estimate this? Yes. So instead of keeping track of the exact time that a page to frame mapping was used, we can instead have a bit, and there's a big difference between storing an extra bit and storing an extra integer. So we could use a bit to just say, since the last time we checked this bit, have you been used? And we call this the use bit or the reference bit. And the idea is every single time that the MMU translates an address on that page, so every time it uses that page to frame mapping, the MMU will set the use bit to 1. It doesn't check the use bit. It doesn't reset the use bit. It simply sets it to 1. And then periodically on a fault, the kernel will clear use bits. It's an interesting idea. So this is fairly simple logic for the MMU. All it has to do is set a bit to 1. It doesn't have to worry about clearing it. It doesn't have to worry about incrementing a counter or setting the time. So the use bit is a much cheaper alternative. Now, how can we use this? Now, this is normally where people are like, oh, look, some pseudocode. We can use this pseudocode to figure this out. I'd actually like to draw the clock replacement algorithm, which is one way of using the use bit, in our notebook here. So let's go over here. I want to erase all this. go. All right. So I'm going to draw a very badly shaped clock. It's called the clock algorithm for a reason. So instead of thinking of our memory as, a rectangle, let's think of our memory instead as a clock or a pizza, whatever you prefer. So here's our clock. Now let's cut it up like a pizza. There we go. And I'm going to use the inner track for the use bit, and we're going to set the use bits in red. Ooh. That was a really bad line. Okay. So there's our use bits, and these are our pages that are loaded into the frames. Now we have this thing called the victim pointer. And the victim pointer is going to start at the first frame. So let's suppose you have a page fault. And we are trying to access page K. We need to see that physical memory is full. And so we need to choose one of these 8 pages to evict. So what I'm going to do is my victim pointer points at A. And I'm going to look at the use bit, and I see that it's 1. And that means since the last time I tried to replace this one, this was used, which means this was used fairly recently. So what I'm going to do is I'm going to clear the use bit, set it to 0. And then I'm going to advance that victim pointer to the next one. And I look at its use bit and I see it's also 1. So I'm going to say this is probably not a good one to select because it was used fairly recently. Let's reset it to 0, and then we'll increment our victim pointer again. So we increment the victim pointer, and again we get at C, use bit is 1, so we set it to 0, and we increment our victim pointer. There's our victim there. We look at the use bit. It's 0. That means since the last time D's use bit was cleared, D was not used, which means D has not been used recently for our definition of recent. And so I know this means that D is the good one to evict. So I'm going to evict D here. Of course, now I've got the wrong one. And I'm going to insert my new page K into here. And then I'm going to increment my victim pointer to the next one. And I'm going to then return. Now you'll note I didn't set the use bit to 1. And that's because I'm going to let the MMU do that. So the MMU we would retry this instruction that caused the page fault. When we retry the instruction, the MMU would perform the translation and then set that use bit to 1. So the MMU sets it to 1 and the kernel clears. And then we go on from there. If there's another page fault, let's say now we want to add J, then we would start trying to find a page from here. We'd go E, F, G, and then we'd put J into where H is. So that's how the clock replacement algorithm works. It's kind of neat, right? And all we needed was an extra bit. Now a question I get asked is what happens if the clock looks like this? Every single page was used since the last time it was cleared. Won't this run in a circle forever? And the answer is no, because you stop once you hit a 0. And as you go around the clock, you are resetting all of the use bits to 0. So if they were all 1 to start with, as you go around the clock resetting things to 0, you'll end up back at the start and you'll end up victimizing the original one. So it's not an infinite loop at all. All right. So that is actually the end of on-demand paging, and it is also the end of virtual memory. Now, I know assignment A2A's deadline has passed, but just a few notes. If you didn't manage to get all of A2A working, make sure that you take an effort to get those functions working for A2B, as I mentioned before, because A2B is going to retest all of A2A. So there are 18 of 50 marks dedicated purely to just testing A2A. And then the A2B tests rely on A2A working as well. So it's really important you get that working as best you can. We're not going to talk about assignment 3 anytime soon. It'll probably be just after A2B's deadline, or maybe just right around that time that we talk about assignment 3. You now, as of this moment, actually have everything you need to move on to assignment 3, though, if you are that far ahead. So, on our next episode then, we're going to start a new topic, and it's quite a short topic, and that topic is scheduling. And that is, how do you choose which thread gets to run next? And there's lots of interesting algorithms out there to discuss this particular problem. So we will see you on Thursday for episode 16.
Unix is the most advanced operating system in the world.
The best operating system, real-time operating system available.
Just a much nicer real-time operating system.
Cisco is proud to work with such an innovative product.
It's poised to be a leader in a very exciting marketplace.
It has superior technology, great people, and they understand the markets.
A professional company with a quality product.
3 different groups in IBM have looked at the RTOSs that are in the market today. 3 different groups have come back and said the QNX neutrino represents the most elegant, the most advanced architecture.
We'll be repeating the words architecture several times.
Architecture.
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 It's architecture.
Architecture.
Great architecture.
It enables you to create a better product,
Easy to work with.
Very open.
High performance.
Very easy to develop software too.
high reliability.
Reliability.
Reliable.
Reliable. In the space shuttle, you absolutely need reliability. Fast time to market.
Faster time to market.
It cuts your time to market in half, and it gives you a competitive advantage. Those basic things people are looking for.
With QNX, the possibilities are endless.
I think the technology represents the future of real-time operating systems.